Questions about anything from last time? Oh, thanks. Let's see, so last time I promised to talk about why the Fourier series at a jump converges to the midpoint of a jump. So let's see. And I told you that if you understood this thing that has sort of the quintessential jump, that's the function that's -1 to the left of the origin and +1 to the right. So it's a square wave function. A typical thing for electrical engineers to do is to extend that square wave as a 2-pi periodic thing. And that's the voltage you would get if you flip a switch between plus and minus voltages. You could make it go from 0 to 1, and then it would be like flipping a switch on and off. Anyway, and of course, square waves happen because of that fact. They're very simple to generate with a switch. And so one of the annoying things for electrical engineers, they want to combine alternating circuit, what is it called? Oscillating voltage, the way you get electricity out of the wall. They want to combine those to get a square wave. And if they use Fourier series, it has that annoying Gibbs phenomenon. And but the interesting thing about Fourier series at a jump is they converge. This one converges to the midpoint. And that's a very easy thing to see for that particular Fourier series because it's an odd function. So I told you last time, an odd function would have all the cosine terms be 0. And of course, the constant term is also 0 because the average of that function is 0. And so the Fourier series only involves sine functions, which all vanish at 0. So they add up to 0, that big red dot there. So I claim that understanding that is going to make you be able to understand any jump. Let's think about the case of a jump at the origin. So case, a jump, not necessarily from -1 to +1, but some kind of jump at x equals 0. So let's see, we have a piecewise C1 function. So that's what I want to study now, piecewise C1 functions. And so the picture might look like this. It might have other jumps. But let's say at the origin it jumps from here to here. Let's call this G of X. Okay, so that has a jump from something to something. Let's call this jump amount H for the height of the jump. If I ask myself, how would I make a function that doesn't have a jump? By combining the two things there. And so if you think about it for a little bit, you realize, let's see, g of x jumps by amount h. And j jumps by an amount 2. So I claim that if I subtract h over 2 times j, doesn't jump at that point. That kills the jump. All right? J would have jumped by 2 from -1 to +1. And if I divide it by half, then it would jump from -1/2 to +1/2 with a jump of 1. And so if I subtract that jump, there's no jump. If I multiply it by h and subtract. So convince yourself that this has no jump at x equals 0. Okay, but it might have a kink. Looks like the way I drew it, it doesn't have a kink. Let me make it have a kink. The kink would mean that angle suddenly changes. It's differentiable, but the angle suddenly changes there. So, but it might have a kink. And remember, this is piecewise C1, so it's going to be one of those kinks. It's a corner that we know is the Fourier series converges even at that kind of kink. But it might have a kink at x equals 0. So a kink, that particular one would probably look something like this. Maybe I should just copy it. I don't have to be that fancy. So what would the kink look like? It would be coming in like this, and then the kink would go down like that at x equals 0. So there'd be a corner, like singular spot there. But we know that for piecewise C1 smooth things, we know at a kink of a piecewise C1 smooth the Fourier series converges to the value. So the Fourier series, of g minus h over 2 times my basic jump function converges to the value. Let's see, the value of that function is g. G from, let's see, what is it? Converges to the limit as x goes to 0 from the minus side of g. And so this is, when you combine that with everything you know, let's see, and the Fourier series of this is equal to the Fourier series of g minus h over 2 times the Fourier series of j. And so you combine those two facts, and so you conclude very simply that the Fourier series for g converges to the midpoint of the jump when you put it all together. Of the jump at x equals 0 at least. Well, it's natural to think about what do you do if you're not thinking about 0. So here's how, I'm not going to dwell on this, I just want to explain that it's actually routine. How to extend the idea to jumps at points, at x unequal to 0 points. So the idea is to do is to translate. So let's see, step 1. Extend f to be a 2 pi periodic function. F to be 2 pi periodic. Step 2, think about translations. So that's a fancy term. If you've done Laplace transform or anything like that, you would have studied Laplace transform of the translations of the function. So here's what I mean by translation. You just shift it over. So I'll call translate by a of f at x is what you get when you take f of x and shift it by a distance a. That would move the origin to what? A. It's kind of like moving the origin to, because at the point x equal a, that would be f of a minus a. That's f of 0. So it picks up your graph and moves it a to the right. Oops, sorry. So this moves graph of f a to the right. Okay, so now you make a wild guess. Guess what the Fourier series of the translation goes to. So you guess. We guess that the Fourier series for the translated function is, so I'm guessing this, Fourier series for the translation of f is the translation of the Fourier series. It's correct, and it's a very easy thing to check. You just write out the formulas for those two things and say, sure enough, that is the case. Of course, you have to use the sum of angles formula for, so it's correct. Easy to check. And you need formulas for cosine n times x minus a and sine x n minus a to work out all the details. And you need to change variables in the integrals. And change x minus a to be equal to the variable u in the coefficients, in the formulas for coefficients. Anyway, it's straightforward and you just do it. Anyway, that means if you have a jump at some point like A, you just move that to the origin and you know what happens there, and then you move it back to A. And so it follows from this that the same behavior at x equals 0 holds at other points. So I didn't want to get bogged down doing all the gory details because they're kind of routine. The idea is very simple. If you understand it for that one test thing, you understand it, period. Questions about that? Yeah.
Earlier when you said the split up the Fourier series of fx minus
Right.
into the two parts, like don't you have to have both of those quantity and Fourier series converge in order to split them up like that?
Well, let's see. When you do that, there's no more jump, and there's a kink, and so you figure out what it converges to, and then you use the fact that G has two different limits from the left and the right, and J has two different limits from the left and the right. And when you calculate the left and the right, you see it, and solve for the G one, you see that G does exactly what it's supposed to do. Sit down and think about it for a while. I didn't want to write it out in gory detail. Okay, now I want to do something fun today. And solve the hot wire problem. It's a good time. Now that we've been doing all this hard work, it's exciting to see what this stuff is good for. So the hot wire problem is, I've got a hot wire. It's a one-dimensional wire. I'm going to stretch it from 0 to L along the x-axis. And I'm going to let the temperature in that hot wire be U of xt equals temperature at x at time t. Well, the one-dimensional heat equation, one space dimension heat equation, is du dt equals constant, which depends on things like the thermal conductivity and various other things, of d2u dx squared. So that's different than the wave equation. The wave equation had a second-order derivative on the left. This looks easier. It's got a first-order derivative on the left. So the t problem is going to be easier this time. And actually, the t problem leads to a very rapidly converging thing. Okay, so that's the PDE, partial differential equation, that governs the problem. By the way, I'm going to derive the heat equation from first principles next time, just so you see it. Everybody should see it at least once. Stein does it in the book. Okay, so let's see if this is going to be a reasonable problem. That's a real wire, and we want to figure out what the temperature does. So if we're going to figure out what the temperature does, we need to know what it starts out as. So we're going to be given the initial temperature of the wire. So that would be u of x at time 0 is some known function. So let's call that f of x. And we know that temperature. It'll also be relevant what happens at the endpoints. I'm assuming it's insulated, so no heat is escaping through the sides. It can only travel left and right. So we need initial conditions and we need boundary conditions. And I'll take the simple ones. These are called the homogeneous boundary conditions. So initial and boundary. And we'll take the boundary conditions to be U on the left end point is being held at 0 degrees. And U at the right end point is also being held at 0 degrees. These are known as the homogeneous boundary conditions, because if I had two functions that satisfy that and add them together, sure enough, they satisfy the same condition. So that's an important thing for us. These are called the homogeneous boundary conditions. Because homogeneous has lots of meanings in math. In this case, it doesn't mean uniformly something. It just means zero, so that when you add two things together, they're still zero. Like homogeneous ODEs. Let's see. So, naturally, anybody who's been around the Bernoullis for any amount of time would suggest to try the method of separation of variables. So we're going to try functions of the form function of x times a function of time. And so if step one is plug it in the PDE. Let's see, I'm going to take I guess I'll keep my C, what the heck. That C is positive, by the way. It's a physical quantity that's positive. So the PDE is, I want du dt to be equal to C times d2u dx squared. And when I calculate the t derivative, that just piles the derivative onto the t function. And it's an ordinary derivative. And so I want that to be equal to, the x derivative here would pile onto the x function. And the t would just sit there like a constant. And then you look at that for a second and think, oh, I can get all the t functions on one side and all the x functions on the other side. So you get t prime over t equals, where am I going to put the c? I think I'll put the c on the t side. The x side is going to be harder because it's a second order equation. Okay. And of course, you know what happens here. In order for a function of t to be equal to a function of x, they both must be constant. And we see that by, how about set x equal L over 2. See, the t function is constant. See, the left is constant, left side constant. So if the left side's constant, the right side has to be constant too. So the right side must be the same constant. Okay, so put that in the box maybe. Well, the t problem is the easy one. This is a very simple constant coefficient first order linear differential equation. It's even homogeneous because it's 0 on the right hand side. So that's the t problem. I'll save it for last. It's the boundary conditions that affect the number of solutions we're going to have. So I'll call this the t problem. It's easy. Let's save it for last. The x problem is going to be interesting. Let's see. It's so easy, why don't I just do it? Yeah, let's see. What is it? That's t. You learned how to do this in freshman calculus. T prime equals lambda ct. That's exponential growth or decay. So remember, population growth and radioactive decay both satisfied that kind of thing. And so the t function is a constant. I'll call it k since I've already got a c. K times e to the lambda ct. Okay, so we've got that one all figured out. That's what it has to be. So now we think about the x problem. That's where the interesting stuff is going to happen. That t problem had no bearing on what lambda could be. But the x problem, it's the boundary conditions that are going to affect. This is where the boundary conditions come in. I'm not thinking about the initial conditions yet because I'm going to do that last when I can add stuff up and get more solutions. So the boundary conditions are u of 0 at all time. Let's see, that would be x of 0 times t of t. We want that to be equal to 0. Similarly, at the other endpoint, that would be x of L times t of t to be identically 0. Well, we certainly don't want t of t to be identically 0 because then that would give us the 0 solution. So we need those two things. We don't want t of t to be identically 0. We know the 0, if you have an ice cold wire and let it sit there, it's going to stay ice cold. We know the 0 solution. U of xt is identically 0 is a solution. That's easy to check. So we must have those other two things are 0. So we must x of 0 equals 0 and x of L equals 0. This is another one of those boundary problems called a Sturm-Liouville problem. So the x problem is familiar to us. It's x double prime minus lambda x equals 0, subject to the boundary conditions, x of 0 equals 0, and x of L equals 0. That's a Sturm-Liouville problem. And in fact, we know how to solve it. This is the one thing you solved in your homework. I'll review quickly what the answer is. Let's do the case first, lambda positive. Then we'll write lambda equal k squared, where k is positive. Then my characteristic polynomial, let's see, if we get x double prime minus k squared x equals 0. And when you plug in x of x equals e to the rx, guessing that is the solution, your characteristic equation is r squared minus k squared equals 0. And so you get r equals plus or minus k. And the general solution is x of x equals c1 e to the kx plus c2 e to the minus kx. And if you want x of 0, let's see, x of 0 is c1 plus c2. And that's got to be 0. So that tells me that C2 is minus C1. And now, so that means that x of x is c1 times e to the kx minus e to the minus kx. And now that, so here's first thing we need. The second thing we need is that x at L, now we know that would be c1 e to the kl minus e to the minus kl. We want that to be equal to 0. But this is 2 times the hyperbolic sine. If I divided that by 2, it would be the hyperbolic sine. Hyperbolic sine of k times L. And of course, the graph of the hyperbolic sine looks like what does it look like? It blows up. It's negative to the left and positive to the right, but it goes blows up. Not like sine, but like exponential. When it blows up really bad. Is that what it looks like? I think so. So let's see. It would look like, that's probably more what it looks like. Hyperbolic sine function. Because when it blows up like exponential, of course, it's going to be concave going up. And so it's 0 at the origin, but it's never 0 for a positive value. So here's KL somewhere. That's KL is positive. That's not 0. In fact, it's strictly positive. And so that we have to conclude that C1 is 0. So ouch, all we get is the 0 solution. So that's not a case that's of interest to us. So we only get the x of x equals 0 solution again. Okay. The next case is lambda equals 0. Then the ODE is x double prime is 0. And you integrate twice, you get x of x is a constant, a. Integrate again, you get, x prime of x is a constant. Integrate again, and you get a of x of x is ax plus b. And if you try to make the boundary conditions hold, let's see, ax plus b is a line of slope a going through b. And we want this function to go through, be 0 at 0 and 0 at L. And the only line that goes through that is the one that's identically 0. And A and B must both be 0. X of x is identically 0 again. Okay, so before we panic, we know something wonderful is going to happen in the case that lambda is negative. Then we'll write lambda equal minus k squared. So I don't have to write square roots of lambda. Actually, I'd have to write square roots of absolute value of lambda, which is even worse. And of course, k is a positive thing. Then the characteristic polynomial is r squared plus k squared equals 0. And we've gone through this enough times that we know we'll get x of x equals c1 cosine kx plus c2 sine kx. And so now we think about the boundary conditions. X of 0 is c1 plus c2 times 0. And so right away we see that, oh, we want that to be 0. c1 has to be 0. So that means that x of x is c2 times sine kx. Looks like we're in danger of getting the thing being identically 0 again. So this is the number 1 boundary condition. The number 2 one is x of L. That would be c2 sine kl. Well, unlike the hyperbolic sign, the trigonometric sign can hopefully wiggle around and be 0 there. So we want that to equal 0. It might not necessarily happen for any old k, but for certain k it would, because the sine function vanishes at multiples of pi. So sine function looks like this. This is pi. This is 2 pi, 3 pi, etc. And this is a graph of sine of t. Why not? So let's see. Sine. We'll have this. We certainly don't want c2 to be 0 because that would give us the 0 solution. So we must have that the sine thing is 0. Sine KL is equal to 0. And that means that KL is a multiple of pi. Of course, KL is a, let's say it's a positive thing. So if it was here, it wouldn't be enough. That KL doesn't do it. But if KL is pi or 2 pi or 3 pi, it does do it. So we need, we don't have 0 pi there because KL is a positive thing. So K pi, KL needs to be a multiple of pi, n pi, for n equal 1, 2, 3, etc. And so K is n pi over L. Let's put that in the red box. Remember, lambda is K squared. That means the lambdas can only be n pi over L squared for n equal 1, 2, 3. Those are the only ones that are going to give me solutions. What? You're right. Lambda. Did I have a minus lambda? Yeah. Right. Lambda was minus k squared. Thank you. So it's minus that. Oh, that's interesting. It's important that lambda be negative. And I'll explain why in a second. The negative sign here is going to be very important. So it's going to mean those exponential functions die away very fast. So let's see, what did I get? I got a solution. Let's see. Remember my, let's take the C2 to be 1. We know C1 is equal to 0. I'm telling you why. I'm going to take C2 to be 1. And it's okay to do that because later we will take linear combinations. to deal with the initial conditions. So I got a solutions. So we got, I'll call it un of xt is sine n pi over L x. Times my t function. Oh, let's see, I should move it over. I like to put my t function in front of the sign. What was my t function? It was e to the minus lambda ct. Was that what it was? Yeah. It was e to the no, it was e to the lambda ct, and lambda is negative. So, and not only that, it's the square of an n thing here. So that's a big number, t. Those go to 0 really fast because n squared, and you take e to the minus n squared times something, those are going to make the things converge like lightning. And so the solution to the heat problem is going to have fantastic convergence. Okay, so a very important facts, the PDE is linear. And the boundary conditions are homogeneous. So we can add solutions together and get more solutions. That's the superposition principle. Okay, so finally, the moment has arrived to think about the initial conditions. Finally, let's worry about the initial conditions. And of course, if I take a finite sum as n goes from 1 to capital N of, I'll put here AN's coefficients, e to the minus n pi over L squared C. Did I have my C in my previous one there? No. I should have a C. There was a C here. I should have said let C be 1, but real engineers never would let C be 1. Minus C n pi over L squared T sine n pi x over L well, of course, you can't make, if you take a finite sum there, you're not going to be able to make the initial conditions happen. When you stick in t equals 0, all those exponentials would be 1. And you'd be trying to get a Fourier series, finite Fourier series, that adds up to your initial conditions. So, of course, we need the n to go to infinity. If f is not a trig polynomial. If f of x is not, in fact, a sine function, a trig polynomial of a special form. So it's not a trig polynomial with only sine terms. Okay, so of course, so the solution is going to be u of xt is this Fourier series. I won't recopy it. Okay, so now I'm going to think about the initial condition. U of x at time 0, look at those things. All those exponentials are e to the zeros when I stick in time equals 0. And so that's equal to the sum. Now I'll let n go to infinity of an sine n pi x over L. That's a Fourier series. It's not our usual ones. I want that to be equal to f of x. Well, there's two ways to get the Fourier series. This is a Fourier sine series. And I could go back, like I had never done this before, and show that those are orthogonal functions. Or I could take the formulas I know for Fourier sine series and scale them. So there's two things we could do here. Two things we could do. My favorite would be show those functions are orthogonal. N pi over x over L are orthogonal on 0L. Invent Fourier series, a new Fourier sine series. It works fine. So a new Fourier sine series on this new interval. That works great. Or I could scale the formulas I know to 0L. Let's see, how would I do that? Or scale 0 pi to 0L. And do a change of variables. And change variables in the Fourier sine series formulas. Well, either thing I do is going to bore you to death, so I'm not going to do either. I'm just going to tell you how it works great. So let's see, or scale it to and change variables in the Fourier sine series formulas. So that what I would take here, I would take 0 pi maps to 0L under the change of variables. X goes to pi x over, Lx over pi. When I get to x equal pi, it spits out L. And when you do that and do all the change of variables, either one of those, you get that the ANs are the Fourier sine coefficients. What are they? It's amazing how similar they look to the regular ones. It's like you get the same thing, but you put a pi where the L is. You put an L where the pi is. So that'd be 2 over L, integral from 0 to L, f of x, sine n pi x over L.